All right. That complex voltage is proportional to complex current at any instant. Look that that expression resembles Ohm's law. So whatever relationship we derive for resistors is valid over here. If we connect two elements in parallel, we can calculate complex impedance because the proportionality coefficient between complex voltage and complex current is complex impedance. So equivalent complex impedance would be calculated like equivalent resistance was calculated for system of resistors. Actually, if we recognize also that current and complex current and complex voltage, they both have factor e to I omega t. So if I divide both sides by e to I omega t, well, what will be left over here is the, well, we call it complex amplitude of the voltage, and this expression over here is the complex amplitude of the current. So I can also recognize that complex amplitude of the voltage is proportional to complex amplitude of the current. All right. So let's now take a look at just for connections in parallel and in series, how we can find out equivalent complex impedance of elements which are connected in particular way. So now I don't want you to think about that these are two resistors. Let's say one is a resistor, one is an inductor, or we have a capacitor and inductor. If elements are connected in parallel, it means that the potentials on corresponding sides are equal, right? This is what defines a parallel connection. And in this situation, current entering the entire system is equal to the sum of currents entering individual elements. Now, complex current and complex voltage are defined in such a way that the vertical component of the phasor represents the real current. So this current, for example, is a projection of the phasor on the vertical line. In other words, it is real part of complex current, and each of them is real part of complex current flowing through the other elements. Now, when we add complex numbers, we separately add real parts and separately add imaginary parts. Therefore, I mean, imaginary part of the sum is equal to the sum of imaginary parts. Can you repeat it? And think about it. What did I say? That imaginary part of the sum of two complex numbers is equal to sum of imaginary parts. Is it true? Show me an example. Just an example that it really works. So let's take one complex number. Give me a complex number. Any. 1 plus I, for example, okay? 1 plus I. And another complex number. Give me another complex number. 4 minus 3I. Okay, now when I add these two numbers, what will be the real part of the resultant complex number? Shout. 5, correct. How did you get it? We added 1 and 4. Why 1 and 4? Because this 1 is a real part of the first complex number. This 4 is the real number, a real part of the second complex number. All right, now, so we are adding here real parts. Now, what will stand next to I? Minus 2. How did we get that? Well, we added 1 and minus 3, right? So we are adding separately real parts to get a real part, and add separately imaginary parts to get the imaginary part. All right. Yes, I could indeed write that imaginary part of Z1 plus Z2 is equal to imaginary part of Z1 plus imaginary part of Z2. All right, now it isn't necessarily unique statement, but if I will assume that if imaginary parts agree, then that the complex numbers agree as well. Although it is not true in general, because real parts don't have to be. But for simplicity of calculation, I can assign those functions in such a way that real parts agree as well. All right. Now, according to the definition of complex impedance, I can recognize that this derivation now is identical like what we did for resistors connected in parallel, because previously we had a real current over here and replace it by the voltage across the resistor divided by resistance of the resistor. Now I have an arbitrary element and complex values. So I take complex voltage across the element divided by complex impedance of that element. Yet this is not Z1, Z2, and Zn are complex impedances of the elements, and I can factor it out in front and recognize that the equivalent complex impedance of elements connected in parallel is equal to inverse of the sum of inverses. Let's actually think about a problem. I mean, I'm going a little bit. I will go with this a little bit ahead. But if we have an inductor, complex impedance of an inductor is a function of frequency of the current flowing through this inductor, and complex impedance of an inductor is equal to I times angular frequency of the current multiplied by inductance of the inductor. Complex impedance of a capacitor is equal to minus I divided by angular frequency times capacitance of the capacitor. Let's say that I will have two elements. I will take an inductor and a capacitor, and I will select such a frequency that they both have equal complex impedance. How about if we have that impedance is 1 kilo ohm, which means that complex impedance of the inductor will be I kilo ohms, and complex impedance of the capacitor would be minus I kilo ohms. Now, I connect those two elements in parallel. So let's find out what is equivalent impedance of this entire arrangement. Well, so from this expression, I can find out that the complex equivalent impedance is equal to, well, I have to take inverse of complex impedance of the inductor, so it is 1 over I plus 1 over minus I to minus 1. Actually, it's easy to find, yeah, because I mean, I can take this minus over here, and I will have 1 over I minus 1 over I. So how much is that? 0, and I take inverse of that, so the result is 0? No. 1 over 0 is not 0. Infinite. So equivalent impedance of this circuit is equivalent complex impedance is infinite. Well, now how complex impedance is related to impedance itself? Yeah, it was on the previous slide. So equivalent impedance of this circuit is, well, always absolute value of complex impedance, so it's still infinite. All right, so if root mean square value of the voltage over here is 1 volt, determine the current flowing through this. What is the value of this current here? How much? How did you get it? You are right. It's 0. Who said that? How did you get it? Correct, because equivalent impedance, it's root mean square value of the voltage divided by root mean square value of the current. Now this value is 1. This one is infinity, which means that current had to be 0. Current would not flow through this branch. Actually, this circuit is very important because we have an electronic circuit to which we can not apply 1 volt. We can apply only a current, voltage of an order of 1 microvolt. Just think what will happen if I apply 1 microvolt. It will be still 0. Current always will be 0. It doesn't mean actually that current doesn't flow through these two elements. What it happens is that whenever current in the inductor flows to the left, current in the capacitor flows to the right. And when this one changes direction, this one changes direction. The currents in those two are always equal in this situation. So currents flow in both, but they add up to a 0 current because they always flow in the opposite direction. So we apply alternating, source of alternating voltage over here, and we make current to flow, to get crazy in that loop, going only back and forth. And actually that thing is used to receive radio waves. Because a broadcasting station produces here very weak electric field. So if I take, for example, a rod, potential difference between this part and this part is tiny. But if I put the circuit over here, I can get quite large currents flowing in that circuit, although current doesn't flow through entire system. We will talk about this circuit pretty soon. All right, let's now take a look what will happen if we connect elements in series. Well, then voltage across the entire system is equal to the sum of voltages, and I can say the same thing about complex voltages. When elements are connected in series, then current through each element has the same value, which means that I can represent each of the voltages as a product of complex current flowing through an element and complex impedance of that element. And I can factor it in front, which means now that equivalent impedance of this circuit, complex equivalent impedance, is equal to the sum of impedances. Well, why don't we actually think about the situation from the same two elements? So this time I connect a capacitor and an inductor in series. So what will be equivalent impedance now of this circuit? 0, correct? Because complex impedance of the capacitor is minus I, complex impedance of the inductor is I. Minus I plus I gives me 0. And if I take absolute value of that, in order to find impedance itself, I will get 0. Right. So what can you say? I mean, if current 1 milliampere flows here, what's potential difference between this point and this point? We say? I think I heard the word. It's 0. Yeah, because I multiply current by impedance, which is 0. It gives me voltage across the system. So voltage across root mean square value of the voltage across the system is going to be 0, even though current flows. Now, how about voltage across this element? Root mean square value of the voltage across this element. How much is going to be? -1. I mean, if I take, if this is point A, this is point B, so VA minus VB is going to be -1 volts. Right. Now let's say that this is point VC. What about VC, VB minus VC? What is, in other words, what is voltage between these 2 points? Root mean square value of the voltage across the inductor. How much is going to be? 1. Right. So it's going to be 1 volt. Well, root mean square value actually can never be negative. Sorry, this is. It's not potential difference, right? It is root mean square value. All right, so root mean square values are 1 volt. So we have, if we connect actually, because if we use a meter, a voltmeter or an ammeter, they are always, the scales are made in such a way that they measure root mean square values. So if you buy a meter in Strassers or an electronic shop and plug it into the socket, it will measure 120 volts. This 120 volt is the root mean square value. It always measures root mean square value. So if I take a voltmeter and connect it between these 2 points, I will get 1 volt. Between these 2 points, I will get 1 volt. Between these 2, and I will get 0. Right. Now, how is it possible that voltage across, I mean, now I will use technical slang. How is it possible that voltage across this element is 1 volt, voltage across this element is 1 volt, and voltage across the system is 0? Because I'm talking not about voltage. What am I talking about? Root mean square value of that voltage, correct. Now, if I spoke about voltage, I mean, this is what I would have, that I would, when I had -1 over here, I would have +1 over there. The 2 voltages will always be the instantaneous values of this V of t. They would be always opposite, and they would add up to, therefore, they would add up to 0. All right. Now we have actually to figure out how elements behave when they are, I mean, all 3 elements. So let's start with a resistor. I mean, I will bring up actually these relationships now. So if we have a resistor, now let's start with a real analysis. So we will think about real current and real voltage. In a resistor, current and voltage are always proportional to each other. So if I take a current, a sinusoidal current, so it will be peak value of the current multiplied by sine of angular frequency times time plus initial phase of the current. So if I want to find out voltage, to relate it to voltage, I have to multiply this expression by resistance, because a resistor is an element that voltage at any instant is proportional to current at the same instant. So then I would get such an expression for the voltage. Yeah, now recognize that Im is the peak value of the current. Delta I is initial phase of the current. Now I related that current to voltage, so what is the peak value of the voltage? How is it related to peak value of the current? Yeah, in order to find out what is the peak value of an electrical quantity, I have to write electrical quantity. Let's say that I take an electrical quantity psi. I have to write it down in that form. When I wrote it in that form, I can identify what is the peak value of this quantity and what is the initial phase of that quantity. How? How do I see that over there? Let's say that, I mean, for this alternating current coming out from the sockets, I would write over here that this is 170 volts times sine of angular frequency is 2 pi times 60 hertz times t, and I will put 0. I can choose it in an instant 0 in such a way that it would agree. What's the peak value of this voltage? 170 volts. How did you figure it out? Well, it's whatever stands in front of the trigonometric function. The number in front of the trigonometric function says what is the peak value of that quantity. Now, what's angular frequency of this voltage? Not 60 hertz. This is frequency. 60 hertz is frequency, which is correct. But I'm asking about angular frequency, omega. How much? How much? 120 pi. I buy that. Yeah, you can say 2 pi times 60. Whatever stands in front of t is angular frequency, right? So this number over here is angular frequency. What's the initial phase over there? 0, right? Because I put it 0 over here. All right. Now, let's come back. What's the peak value of the current? I am correct. What's the initial phase of the current? Delta I, correct. Yeah, these two numbers, the number in front of the trigonometric function says what is the peak value of the current, and this number over here says what is the initial phase. Yeah, so we remember that now, that what is the peak value of the current and what is the initial phase of the voltage and see current, and see how these quantities, what are the values of these quantities for voltage, and how they are related to the values for current. Yeah, so for voltage I have to multiply current by resistance. So if I multiply current by resistance, I will get peak value of the current multiplied by resistance, and that's it. I mean, this function wouldn't change. So my question now is, what is the peak value? I mean, if I wrote a function representing voltage in such a form, from this form tell me what is the peak value of the voltage. Im times R, correct. This product over here gives me peak value of the voltage. This is peak value of the voltage. How about initial phase of the voltage? Delta I, it happens to be identical as for the current. All right, now how about, let's find out impedance of the resistor then. How much? I can't hear you. Not 0.
So the resistor is equal to the resistance of the...
How did you know that? They're not good enough. You have to see it, not remember that you read it.
Potential difference in proportional current.
Nope. Impedance is not related to potential differences. It is related to what? But I mean, you're on the right track. You just, I mean, in a way, I'm trying to be malicious because I know that you know. However, you say it wrong, and I pretend that I don't know. A what? Very good. Peak value of the voltage divided by peak value of the current. All right. So, well, Jeff already said that peak value of the voltage over here is peak equal to the IM, which was peak value of the current multiplied by resistance. And now I have to divide it in order to get impedance. I have to divide it by peak value of the current. What was the peak value of the current? IM, right. So IM and IM cancels, and we get that impedance of a resistor is equal to its resistance. How about relationship between phase? Well, what is the phase angle then? How much is the phase angle? Now we have to recall what phase angle is. And somebody already said 0. The answer is correct. How did you get it? Who got it? How did you get it? Correct. It is difference between the phase of the voltage and the phase of the current. And we could also say that it is between initial phases. Yes, I have to, from phase of the voltage, I have to subtract initial phase of the current. And it happens that in a resistor they are equal. So it's 0. All right. Well, which actually, I mean, what we found is that current and voltage are indeed proportional. So these are, these would be the plots of current and voltage. And actually, if we look at this plot, why don't we try to make an estimate of well, let's say resistance. What is resistance of this of a resistor for which current and voltage would be represented by these two functions? Who says that it will be? I mean, let's say that current is measured in milliamperes and voltage is in volts. So, who believes that it will be 1 kilo ohm resistor? For simplicity, let's make current in amperes. Yeah, current is in amperes, voltage is in volts. So how about if it is 2 ohms? What did you say, Adam? How do you see that?
Well, because you're multiplied by the resistance.
Correct, because if we multiply current by resistance, we should get voltage. Yes, so if I multiply current by number 2, I mean, in other words, the red plot, I will get blue plot. I mean, 2 is actually a very bad approximation. I would say that it's different. What? 1.5. Yeah, about 1.5 ohms. All right. Yes. So. We found that impedance of a resistor is independent on the frequency, and it is always equal to resistance of the resistor, and the phase angle is 0, which means that the phases always coincide. What's impedance of this resistor? What do you say?
1.5.
Also 1.5, because impedance is of a resistor is always equal to resistance. All right. Now I want also to bring up one more aspect of well, electricity. How much power is delivered to an element? So let's estimate average power delivered to an element. And do you remember how we find average power delivered to a circuit? What do we have to multiply by what and by what? It's what? Nope. I mean, in general, not just for a resistor. It's true that for resistors we can multiply square of current by resistance, we can divide square of voltage by resistance, But in general, it's a product of current and voltage. But this gives us instantaneous value of power, not power, Adam. Yeah, now how to find, not the average power, how to find average power? It was expressed in terms of root mean square values. It was root mean square value of the voltage times root mean square value of the current times cosine of the phase angle. And cosine of 0 is how much? 1. So indeed it's a product of root mean square value of the voltage and root mean square value of the current. In a resistor, actually root mean square value has such a physical sense that it is like a constant voltage and current flowing through the resistor, which will produce the same effect as alternating current. And indeed we can express it using Ohm's law. We can relate it to root mean square value of the current and root mean square value of the voltage. All right, so this will be all for today, and see you tomorrow. You know what? I'm thinking I'm not going to give chapter 33 on the test. So, I mean, I don't want to put on the test something which I discuss tomorrow. So, chapter 33 is not on the test. Thank you very much.